This is a simple diagram of GANs. One part is a generator, and the other part is a discriminator. The role of the generator is to use some random noise as input and output a fake sample that is very similar to the real sample. The task of the discriminator is to be able to distinguish whether the input sample is fake or not. As we discussed in class, in game theory, the GAN model converges when the discriminator and the generator reach a Nash equilibrium. This is the optimal point for the minimax equation. JS divergence is symmetrical, unlike KL divergence. It will penalize poor images. GANs is difficult to train. We will face problems like long convergence, diminished gradient. In the high-dimensional space, where the samples are located, it is very easy for the discriminator to perfectly distinguish between fake samples and real samples. At this time, the value of JS divergence will approach a constant. This will cause the generator to no longer be updated. This is also an issue of JSD. Optimizing D too much leads to vanishing gradient. Supervised learning with convolutional network has seen huge adoption in computer vision applications. A class of CNNs called DCGAN are strong candidates for unsupervised learning, but this does not fundamentally solve the problem of unstable GAN model training. In WGN, a new evaluation method called Earth Mover Distance was introduced. EM distance is continuous when evaluating the distance of two distributions, which does not exhibit the abrupt properties of JS divergence. This can make the training of GAN more stable. In addition, the discriminator must satisfy K-Lipschitz continuity. SAGAN allows attention-driven, long-range dependency modeling for image generation tasks. Traditional convolutional GANs generate high-resolution details as a function of only sparsely local points. However, in SAGAN, details can be generated using cues from all feature locations. I use a face dataset, Celebrity A. Celebrity A has large diversities, large quantities, and rich annotations. And I modified these models and trained each model with a fixed epoch. We use two indicators of IS and FID to evaluate different GAN models. Inception score considers both clarity and images and diversity of images. The score is limited by what the inception classifier can detect, which is directly linked to the trailing data. FID compares latent feature from generated and real images. Shortcomings of FID includes it uses pre-trained inception model which may not capture all features, and it needs a large sample size. In this experiment, I use FID to evaluate different GAN models. From the above experiment results, we can see that image generated by SNGAN is better than WGAN and DCGAN. However, FID of WGAN is lower than DCGAN and SAGAN. A lower FID means that two distributions are closer, which also means that the quality and the diversity of photos are higher.